The Standard Model is one of the most successful theories in all of science, and it still can't explain gravity, dark matter, or dark energy. So we're starting this tour of the entire universe on a foundation that physicists themselves admit is incomplete. We can even add layers to it, so let's start with the family that has crazy differences in size: subatomic particles. Physicists organize these 12 particles into a framework called the Standard Model. 6 of them are called quarks, 6 are called leptons. The quarks come in 6 flavors: up, down, strange, charm, top, and bottom. And here's the weird part. Quarks are everywhere, but a lone quark has never been observed. They always travel in groups. The size differences within this family are insane. The electron weighs 0.511 mega-electron volts. The top quark weighs about 172,570. That's the same category of particle, 300,000 times apart in mass. And what gives them mass in the first place? A particle called the Higgs boson, discovered in 2012 with a mass of about 125,000 to 200 mega-electron volts. Without it, none of these particles would have mass, and matter as we know it just wouldn't exist. So what happens when these tiny particles start teaming up? Atoms and molecules. So subatomic particles combine into atoms, and atoms are where chemistry starts. They're the smallest unit of an element that still behaves like that element. Hydrogen, oxygen, carbon, all atoms. But here's the thing, nobody tells you, atoms are almost entirely nothing. The nucleus, the dense core where all the mass lives, is only about 1 to 10 femtometers across. The electron cloud surrounding it extends out to hundreds of picometers. That makes the atom more than 10,000 times wider than its own center. Here's a way to picture it. Take a hydrogen atom, radius 53 picometers, scale it up to the size of a football stadium. The nucleus would be a marble sitting on the 50-yard line. Everything else is empty space. You, me, this planet, we're built from almost nothing. And yet atoms bond together into molecules. Water, DNA, the air you're breathing right now, all of it is emergent structure built from that mostly empty scaffolding. Atoms sharing and swapping electrons, assembling into every substance that exists. So we've got atoms and molecules. But where do they actually gather in space, and what happens when enough of them clump together? Nebulae and the interstellar medium. So atoms exist, great, but where do they hang out? Mostly in the interstellar medium, the stuff between stars. It's about 99% gas and 1% dust by mass, with densities as low as 0.1 atoms per cubic centimeter. That's emptier than the emptiest vacuum we can create on Earth, but stretch that near-nothingness across light years, and it adds up to something enormous. Now, in certain spots, this gas clumps together into dense pockets called nebulae. Gravity pulls these clumps tighter, they heat up, and eventually they ignite into stars. These are literal stellar nurseries. The Orion Nebula is a perfect example. It's about 25 light years across and contains over 3,000 stars, some with protoplanetary disks already forming around them, but it's not peaceful. Ultraviolet radiation from the biggest young stars carves cavities into the surrounding gas, sculpting the nebula's shape and sometimes snuffing out smaller neighboring stars before they even finish forming. And those gorgeous, colorful nebula photos, real but wavelength dependent, swap from visible light to infrared, and the whole palette changes, so now we've got stars being born. But what happens once they actually light up? Stars and solar systems. So all those collapsing clouds and nebulae, they don't just make stars, they make entire solar systems. Ours formed about 4.6 billion years ago, and it contains 8 planets, 5 dwarf planets, and an enormous amount of smaller debris, all orbiting one star. And that star, the Sun, accounts for 99.86% of the total mass of the entire solar system. Every planet, every moon, every asteroid, every comet, all of it combined, less than 0.14%. But here's the thing, our solar system is not special. The NASA Exoplanet Archive currently lists over 6,000 confirmed exoplanets, and the methods we use to find them are biased toward big planets close to their stars, meaning the real count is certainly far higher. The variety is staggering. So what about the planets themselves? What kinds of worlds are actually out there? Planets and moons. So we've got stars, we've got solar systems, but what's actually in them? A lot. Mercury is the smallest planet in our solar system, Jupiter and Saturn together hold nearly 90% of all non-stellar mass in the system. And that's just our neighborhood. The Kepler mission alone confirmed 2,783 exoplanets. K2 added 549. TESS has added 748 and is still counting. These missions are biased toward planets that orbit close to their stars, so what we found is a fraction of what's actually out there. Among those discoveries, 546 confirmed planets have radii no larger than 1.25 times Earth's. But the catalog also includes stuff that makes no sense. HAT-P-67b is a gas giant with a radius over twice Jupiter's, but a mass of only about 0.45 Jupiter masses. That gives it a density below 0.1 grams per cubic centimeter. And then there are moons. Earth has 1. Jupiter has almost 100 confirmed. Some of those moons, like Europa and Titan, are considered serious candidates for hosting liquid water or even life. Speaking of things lurking in the dark that we can barely see, black holes. When a massive star dies, it doesn't just fizzle out. Its core collapses so violently that it punches a hole in the fabric of space itself. The gravity becomes so extreme that not even light can escape past a boundary called the event horizon. No light out means no seeing it. Black holes are, by definition, invisible. So how many do we know about? About 50. 50 stellar mass black holes have been directly identified in the Milky Way, mostly because they happen to be orbiting a companion star and ripping material off it, which releases X-rays we can detect. But here's the problem. Scientists estimate our galaxy alone could contain up to 100 million black holes. We found 50. There could be 100 million. That's like searching a beach for grains of black sand in the dark. Most of them will never be individually detected because they're just sitting there, warping space, being invisible, and they come in sizes. Stellar mass black holes can exceed roughly 20 times the sun's mass. Then there are intermediate mass black holes, theorized between 100 and several hundred thousand solar masses. And then there are the big ones, supermassive black holes anchoring the centers of most large galaxies. Ours is called Sagittarius A star, and it masses about 4.3 million times the sun. The takeaway here is kind of haunting. If 100 million black holes are drifting through our galaxy invisibly, the universe at every scale is way more crowded with extreme physics than any clean diagram would have you believe. So what happens when you zoom out past individual stars and black holes and look at the whole collection? Galaxies. So we've got stars, black holes, nebulae, all sorts of cosmic furniture. But none of it is just floating around randomly. It's all held together in massive spinning collections. Our collection is the Milky Way, and it contains roughly 100 billion stars stretched across a disk about 100,000 light years wide. Our solar system sits about 25,000 light years from the center. And at the sun's speed, one galactic orbit takes about 250 million years. At the center of the Milky Way sits Sagittarius A star. The galaxy itself is classified as a barred spiral. But here's where it gets humbling. The Milky Way is one galaxy. Classic estimates said the observable universe contains somewhere between 100 billion and 200 billion galaxies. Then more recent studies came along and revised that number to around 2 trillion. Each of those galaxies contains billions of stars, and many of those stars have planets. So what happens when you start grouping all these galaxies together? Galaxy groups and clusters. So galaxies aren't just floating around randomly. Gravity pulls them together into collections. A small collection, up to about 100 galaxies, is called a group. A big collection, hundreds to thousands of galaxies, is called a cluster. And these are the largest structures in the universe that are actually gravitationally bound together. We live in the local group. That's us, Andromeda, and about 132 other confirmed member galaxies. The Virgo cluster sits about 53.8 million light-years away and contains somewhere between 1,300 and 2,000 galaxies. Then there's the Coma cluster, over 1,000 galaxies spanning about 20 million light-years, and its galaxies are swimming in reservoirs of hot gas heated to tens of millions of degrees. You can't see this gas with a normal telescope, it only shows up in X-rays. But here's the problem. When you add up all the visible stars and all that hot gas, The math doesn't work. There isn't enough mass to hold these clusters together. Something else is providing the gravitational glue, something we can't see. That's dark matter. So clusters are the last scale where gravity wins. After this, things start to get looser. Superclusters. So we've got clusters of galaxies, hundreds, sometimes thousands of galaxies, all gravitationally bound together. Naturally, the universe doesn't stop there. Clusters themselves clump together into even larger structures called superclusters, collections of clusters, groups, and lone galaxies spanning hundreds of millions of light years. But here's the weird part. Unlike clusters, superclusters aren't actually held together. Dark energy is stretching space between them faster than gravity can pull them back. Our supercluster is called Laniakea, and it was only mapped in 2014. Not by looking at where galaxies are, but by tracking how they flow. Laniakea contains roughly 100,000 galaxies spread across about 400 million light-years. And the Virgo supercluster, which scientists previously thought was our home supercluster, turns out that's just one lobe of Laniakea. Superclusters are arranged in flat sheets and walls. About 10 million superclusters are estimated to exist in the observable universe. Laniakea is one of 10 million containing 100,000 galaxies, one of which is ours. So now, what happens when you zoom out even further and look at how all these superclusters connect? The cosmic web. Okay, so we've got galaxies, groups, clusters, superclusters. Now pull all the way back. And the universe doesn't look like a bunch of stuff scattered randomly through space. It looks like a three-dimensional spider web. Massive filaments of matter stretching across the cosmos, connecting nodes where clusters and superclusters sit, with enormous empty voids in between where there's basically nothing. And these filaments are not small. A single dark matter filament connected to the galaxy cluster Max J 0717 has been measured at least 60 million light-years long. That's one thread. So how do we even see this? We use gravitational lensing. Mass bends light, so when light from distant background galaxies passes near a massive filament, the images get slightly distorted. By reading those distortions, we can map out where the mass is even if we can't see it directly. And here's the best part. Before we could observe any of this, cosmological simulations predicted it. Scientists ran the math, built computer models, and said the universe should look like a web. Then the maps came in. And it did. But the web itself raises a question: what's actually holding it together and what's pushing everything apart? So here's the uncomfortable part. Everything we've talked about so far, every atom, every star, every galaxy, every filament in the cosmic web, all of it makes up about 4.9% of the universe's total content. Dark matter and dark energy, less than 5%. Everything you've ever seen, touched, or measured with a telescope accounts for less than a 20th of what's actually out there. So, what's the rest? About 26.8% is dark matter. It doesn't emit light, it doesn't absorb light. It doesn't reflect light, you cannot see it, photograph it, or poke it with a stick. But its gravitational effects on galaxies and galaxy clusters are so well documented that its existence isn't seriously debated. What it actually is, that part is very much debated. Then there's dark energy, making up the remaining 68.3%. This is even worse. The universe isn't just expanding, it's expanding faster and faster, and dark energy is basically the placeholder name we give to whatever is causing that acceleration. We can measure its effects with impressive precision. We cannot explain it. Missions like Euclid and the James Webb Space Telescope are actively trying to pin down dark energy's properties. The honest summary: we've characterized the universe's composition with remarkable accuracy, and roughly 95% of it is stuff we cannot directly identify. These are the two biggest open questions in all of physics. So what do we actually know about the stage all of this is playing out on the observable universe? Everything we've talked about so far, every quark, every atom, every nebula, star, planet, black hole, galaxy, cluster, supercluster, and filament, all of it fits inside a single sphere about 93 billion light-years across. That's the observable universe. Now hold on. The universe is only about 13.88 billion years old. So how can it be 93 billion light-years wide? Light hasn't had time to travel that far. And you'd be right, it hasn't. But here's the thing. Space itself has been expanding the entire time. Light left the earliest galaxies billions of years ago, and while that light was traveling toward us, the space it already crossed was stretching out behind it. So the source of that light is now way farther away than the light itself ever actually traveled. Inside this sphere, there are roughly 2 trillion galaxies, though that number is still debated. And here's the part that matters most. Observable doesn't mean everything, it means everything light has had time to show us. It's not the edge of the universe, it's the edge of our view. Beyond that boundary, the universe almost certainly keeps going, possibly for an enormous distance, possibly forever. We just can't see it, but that hasn't stopped people from theorizing. The multiverse theory. So we've gone from quarks to atoms to stars to galaxies to the cosmic web to the observable universe. 93 billion light years of stuff. That's everything we can see, measure, photograph, or infer. But some physicists think that's not all there is. Not even close. Before we go further, let's be honest about something. Nothing in this section has a single piece of direct empirical evidence supporting it. Zero. These are real theoretical frameworks developed by serious physicists using real math, but they are, as of right now, completely unverified. Framework number 1. The many worlds interpretation of quantum mechanics says that every time a quantum event occurs, the universe doesn't pick one outcome. It branches, every possible result plays out in its own parallel reality. You didn't just watch this video. In another branch, you clicked away early. Framework number 2. String theory. It predicts a landscape of roughly 10 to the power of 500 possible configurations of the universe. That's a 1 followed by 500 zeros. For reference, the number of atoms in the observable universe is about 10 to the power of 80. Each configuration could correspond to a universe with completely different physical constants. Framework number 3. Eternal inflation. The idea here is that the rapid expansion right after the Big Bang never actually stopped everywhere. In most of space, inflation keeps going, and every now and then, a region pinches off and inflates into its own independent bubble universe, potentially with its own physics. None of these bubbles are reachable from ours. None are detectable. So here's where we are. The math works. The frameworks are internally consistent. Physicists argue about this stuff in journals and at conferences. But without a testable prediction that can distinguish the multiverse exists from the multiverse doesn't, it remains philosophy wearing a physics costume. We started this video with particles too small to see. We ended at the edge of what science can reach and then one step beyond it. The universe, as far as we can tell, has not given us a way to look outside of it, and that is the recurring theme of this whole scale tour. The closer we look, the less final anything seems. Particles lead to fields, atoms lead to emptiness, galaxies lead to dark matter. And the observable universe leads straight to a horizon we cannot cross. Every layer explains the one before it, and then immediately opens a bigger mystery still above it. If you enjoyed this video and want to see more, click the video on the screen now. On the screen now. On the screen now.